A wonderful day to everyone. Before we proceed with our topic, solving systems of linear equation, let us first have a background on round of errors and approximations. Our learning objective for this topic are to understand the concept of error and to know the effective use of numerical methods. So we recall to determine the velocity of the parachutist using exact or analytical method and numerical solutions. Although the numerical technique yielded estimates that were close to the exact analytical solution, there was a discrepancy or error because the numerical method involved an approximation. Although we were fortunate in this case because the availability of an analytical solution allowed us to compute the error exactly. For many applied engineering problems, we cannot obtain analytical solution. Therefore, we cannot compute exactly the errors associated with our numerical methods. In these cases, we must settle for approximation or estimates of the error. So here is a simple introduction. Numerical methods is a process of solving complex numerical problems using simple operations of arithmetic. It yields an approximate results that are close to the exact analytical solution. We cannot exactly compute the errors associated with numerical methods. Only rarely given data are exact since it originates from measurements. Therefore, there is probably an error in the input information or no exact data. Algorithms itself usually introduces error as well. The input information will then contain error from both of these sources. Let's define some definition of terms. Numerical error arises from the approximation to represent exact mathematical operations and quantities. Round-off errors result when numbers having limited significant figures are used to represent exact numbers. Truncation errors is the discrepancy introduced by the fact that numerical methods may employ approximation to represent exact mathematical operations and quantities. Accuracy refers to how closely a computed or measured value to the true value. Accuracy has a negligible error. Precision refers to how closely individual computed or measured value to previously computed or measured values. Inaccuracy or called bias is defined as systematic deviation from the actual or true value. Imprecision, called uncertainty, refers to the magnitude of the scatter. What is the concept of accuracy and precision? Who among you plays target shooting or darts, wherein the center or the so-called bullseye is the target, as we can see in this figure? The dots represents the data either measured or collected. The illustration in A is called inaccurate or imprecise because it is far from the target and the data are also far away with each other or scattered all over. And in figure B, accurate and imprecise data are almost near the target and is still far away from each other but near the target. In figure C, inaccurate and precise, not near the target but near with each other. And in D, accurate and precise, so ito yung mga sharpshooters, so kidding aside, the data are near the target and near with each other. Significant figures. So number of significant figures indicates precision. Significant digits of a number are those that can be used with confidence. For example, we have 8.19 times 10 raised to positive 4, which has 3 significant figures, 1, 2, and 3. And 0.002823, which has 4 significant figures. Bakit 4? We all know leading zeros are not significant. So 1, 2, 3, and 4. Also, significant figure correspond to the number of certain digit plus 1 estimated digits. For example, pi. So 3.14, 15, 92, 65, 35, 89, 79, so on and so forth. Computers retain only a finite number of significant figures. So in computer, pi does not include all these significant figures, such as numbers can never be represented exactly. The omission of the remaining significant figures is called round-off error. Both round-off error and the use of significant figures to express our confidence in a numerical result will be explored in detail in subsequent discussion. In addition, the concept of significant figures will have relevance to our definition of accuracy and precision in the next discussions. Sometimes this data, the full value of pi is not represented or cannot be shown or cannot be stored. So this will cause a round-off error. So error concepts. Relationship between exact or true result and the approximation can be formulated as true value equals approximation plus error. By rearranging, we find that the numerical error is equal to the discrepancy between the truth and the approximation. So, E sub t is equals to true value minus approximation. E sub t is called the true error or the exact value of the error. One way to account for the magnitudes of the quantities being evaluated is to normalize the error to the true value, as in the true fractional relative error equals true error all over true value. The relative error can also be multiplied by 100 to express it as E sub t is equals to true error all over true value multiplied by 100%, which is called the true percent relative error. So let's have an example of calculation of errors. Problem statement. Suppose that you have a task to measure the length of the road and a steel bar and come up with 9,999 and 99 centimeter respectively. If the true values are 10,000 and 100 centimeters respectively, compute the true error and the true percent relative error for each case. Given the true measurement for the road, which is 10,000 centimeter, and for the steel bar, 100 centimeter, and for the actual measurement of 9,999 and 99 centimeters, the required are the true error and the true percent relative error of road and steel bar. Solution for true error, E sub t is equals to true value minus approximation. For the road, E sub t will be equals to 10,000 minus 9,999, which will have a 1 centimeter of true error, and the steel bar will also have 1 centimeter true error from 100 minus 99. We can calculate for the percent relative error. Sub t is equals to true error all over true value multiplied by 100%. So for the road, E sub t is equals to, using 1 centimeter all over the true value 10,000, we will have a 0.01%. And for the steel bar, same 1 centimeter and 100 for the true value multiplied by 100%, we will have a 1% error. So, although both measurements have an error of 1 centimeter, you will notice that the relative error for the steel bar is much greater. So, we could conclude that we have done an adequate job of measuring the road, whereas our estimate for the steel bar leaves something to be desired of. For numerical methods, the true value will be known only when we deal with a function that can be solved analytically. In real-world applications, we will obviously not know the true answer a priori. For these situations, an alternative is to normalize the error using the best available estimate of the true value. That is to approximation itself, as in epsilon sub a is equals to approximate error over approximation multiplied by 100%, where the subscript a signifies that the error is normalized to an approximate value. For example, certain numerical methods use an iterative approach to compute answers. In such an approach, a present approximation is made on the basis of the previous approximation. This process is performed repeatedly or iteratively to successively compute better and better approximation. For such cases, the error is often estimated as the difference between previous and current approximation. Thus, percent relative error is determined according to epsilon A equals to current approximation minus previous approximation over current approximation times 100. The signs of the values of true error and percent relative error may either be positive or negative. If the approximation is greater than true value or the previous approximation is greater than the current approximation, the error is negative. So, let's say this is C sub A, this is PA, and this is C sub A. If PA is greater than CA, therefore, error that will be calculated will be negative. If the approximation is less than the true value, the error is positive. So, if CA is greater than PA, it will have a positive value. For such cases, the computation is repeated until the absolute epsilon A is less than the epsilon S. If this relationship holds, the result is assumed to be within the pre-specified acceptable level or the epsilon S, which has a value of 0.5 times 10 raised to 2 minus negative 1%. If the following criterion is met, we can be assured that the result is correct to at least n significant figures. N is the number of significant figures. Before we have an example about error estimate for iterative methods, let us briefly discuss when a Taylor series becomes a Maclaurin series. Recalling and as shown, function of x is equal to the function of x sub 0 plus x minus x sub 0 raised to 1 all over 1 factorial times the first derivative of x sub 0 plus open parenthesis x minus x sub 0 raised to 2 all over 2 factorial times the second derivative of x sub 0 plus x minus x sub 0 raised to 3 all over 3 factorial multiplied by the third derivative of the function of x sub 0 plus until x minus x sub 0 raised to n all over n factorial multiplied by the nth derivative of the function x sub 0. If x sub 0 is equals to 0, Taylor series becomes Maclaurin series. It will be the function of x is equals to the, instead of x sub 0, it will be the function of 0 plus x, because it will be 0, all over 1 factorial times the first derivative of the function of 0 plus x squared over 2 factorial, the second derivative of the function of 0 plus x cubed over 3 factorial multiplied by the third derivative of the function 0. And so on and so forth until x raised to n all over n factorial multiplied by the nth derivative of the function of 0. For example, on error estimates for iterative methods, in mathematics, functions can be often represented by infinite series. Example, the exponential function can be computed using e raised to x is equals to 1 plus x squared all over 2 factorial plus x cubed over 3 factorial plus and so on and so forth plus until it reach x raised to n all over n factorial. As more terms are added in sequence, the approximation becomes a better and better estimate for the true value of e raised to x. So the above equation is called the Maclaurin series expansion. Let's prove that this equation is a Maclaurin series. So applying the Taylor series expansion, So, function of x, which is equals to, so in order for a Taylor series to become Maclaurin series, we need to assume that x sub 0 will become 0. So then, from this function, we will have the function of x equals to, so we already have the value of the function of 0. Simply by the function of x sub 0 is equals to e raised to x. Therefore, function of 0, so substitute x equals to 0. So therefore, it will have a value of 1. For the first derivative of the function of 0, so the derivative of e raised to x is also e raised to x. So with the function, so same process, so x sub 0, so the first derivative at 0 will also be 1. So for the second derivative, so x sub 0 is also e raised to x. And for the second derivative of the function of 0 will also be 1. So, nagkataon lang na yung ating solution, as you continuously calculate for all the derivatives of e raised to x, it will all have a value of e raised to x. So, substituting the values to this function, so we will be able to have the value as the function of x equals the function of 0 is equals to 1 plus x over 1 factorial. 1 factorial is simply 1. So, we will have here x. And the first derivative at 0 is also 1. So, hindi na natin i-multiply ng 1. Plus x squared over 2 factorial. Multiplied by the second derivative, which is also 1. So, you will be able to have here 3 factorial. Plus so on and so forth. So, you will have here x raised to n over n factorial. So, therefore, for the function of e raised to x, in terms of summation notation, recall the limit and continuity. So, therefore, the function of x equals to e raised to x will have a summation from n equals to 0 to infinity as x raised to n all over n factorial. Thus, we were able to prove that the given series expansion is a Maclaurin series expansion. We have already proved this expansion. If we have here an example of e raised to 0.5, and we are going to calculate for the approximate percent and the true percent relative errors, and starting with the simplest version, e raised to x is equals to 1. Add terms one at a time to estimate e raised to 0.5, wherein, after each term is added, compute the true and approximate percent relative errors respectively. So, we also have to take note that the true value of e raised to 0.5 is 1.648721 and so on and so forth. Terms until the absolute value, the approximate error, estimate epsilon A falls below a pre-specified acceptable error criterion or the E sub S, confirming to 3 significant figures. Before solving the problem, so the givens are the true value of e raised to 0.5 and we're going to confirm up to 3 significant figures. So, what would be the true and approximate percent relative errors? First, we need to find what would be the value of our pre-specified acceptable error criterion or the epsilon S. So, epsilon S from the equation, 0.5 times 10 raised to 2 minus n in percent. So, therefore, 0.5 times 10 raised to 2 minus 3, so 3 from the 3 significant figure, is equals to 0.05%, which can be employed to determine the error criterion that ensures a result is correct to at least 3 significant figures. Thus, we will add a term to the series until epsilon A falls below this level. So, the first estimate is simple, equal to the Maclaurin series with a single term. Thus, the first term is equal to 1. This will be the first estimate. simply the single term. The second estimate is then generated by adding the second term, as in e, so inad na yung pangalawang term, e raised to x is equals to 1 plus x, or for x is equals to 0.5. So, papalitan yung x ng 0.5 kasi yung hinahanap natin na may value ng x ay 0.5. So, we will be able to get the value of e raised to 0.5 equals to 1.5. So, this is the approximation. So, this is the current approximation. As per taking note, so this will be the true value. This represents the true percent relative error of E sub t is equals to true error all over true value times 100%. The true error is equals to true value minus the approximation. So, we will be able to have the value of 9.02%. So, this is simply the true value minus the approximation value and the true value. So, TV minus AB over TV equals to 9.02%. So, using epsilon A, or the percent approximation error, it will be equal to the current approximation minus previous approximation over the current approximation times 100%. For the current approximation, it will use the second approximation, and the previous approximation is the first estimate. It will simply be epsilon A is equals to 1.5 minus 1 all over 1.5. CA minus PA all over CA. So you will notice that the epsilon A value is still greater than epsilon S. So hindi pa natin nasa-satisfy yung equation na less than. Because of that, we still need to have the third estimate and including third term. So, isasama na natin yung ating third term and continued until yung ating absolute epsilon sub A is less than epsilon sub S. So, the entire computation can be summarized as shown in the table. So, let's try using Excel. So, we're back sa ating Excel. I just use the same Excel. So, dun sa ating previous na ginamit. We have here the given Maclaurin series. And with the number of significant figure of 3, we were able to get the value of epsilon sub S, which is also known as the pre-specified acceptable error criterion, has a value of 0.05%. And we're looking at the absolute error of approximation less than the pre-specified acceptable error. We also have the true value of e raised to 0.5 equals to 1.64872121 following the table format as shown on our presentation. So, we're going to try using Excel. Number of terms, result, the epsilon sub t, the epsilon sub a. Epsilon sub t is simply true error over true value times 100. For our first term, or the first estimate, we will have here the single term. So, this will be 1. And for the true percent error, the true value minus approximate value divided by the true value times 100. So, we will have here the value of 39.3569.05. So, for the epsilon sub A, so wala pa tayo kasi wala pa tayong second estimate. So, for the second estimate, so this would simply be the single term as yung ating value of x. And x is equals to 0.5. And same process. So, let's define this as true value. Let's have here e 0.5. So, meron tayong e 0.5. So, palitan natin to e 0.5, 0.5. So, define natin. So, for the value of x, so define din natin x. So, this will be as x. We already have here the second estimate. So, we will have now the value for our Same process. So, the true minus the estimate divided by the true times 100. So, copy lang natin. So, check lang natin. True minus estimate over the true value. And, dito magkakaroon na tayo ng epsilon sub A. So, which is equals to the current minus previous divided by current multiplied by 100. So, ito na, makikita nyo, andito na yung value ating percent. So, 9.02% and 33.3%. You will notice sa approximation, dapat ang ating approximation ay less than. So, dapat ito ay less than sa ating 0.05. So, nagkataon na malaki pa yung value niya, which is 33.333. So on and so forth. So, we'll use now or we will have the third one. Makikita nyo, ito na yung ating two terms used. So, 1 plus x. So, ito na lang din ang gagamitin natin para i-add na lang natin yung ating sunod na equation. That would be x raised to 2. And take note that 2 factorial is simply FACT 2. So, this would be the value for our 3 term or the third iteration natin. So, meron tayong tatlong term na ginamit hanggang 2 factorial. So, same procedure. So, copy natin. So, check na true minus the estimate over true value for the percent relative error. And for the percent or the approximate percent relative error, this would be the current minus previous over the current. The fourth, so meron tayong apat na term. Yung pang third naman ang gagamitin natin. And this will be x raised to 3 divide 3 factorial. So, same procedure. Epsilon sub t, epsilon sub a. Kita nyo, hindi pa tayo less than 0.05. So, we'll use the fifth term. So, for the fifth term, nakikita nyo na wala na siya dito. Ang gagawin na natin will be yung fourth and using summation notation. So, magkakaroon tayo ng idea na ang sunod will be raised to 4 divided by 4 factorial. So, makikita nyo dito, 3 factorial yung una, tapos 4 factorial yung sunod. Based yun sa summation notation. So, dun ka magkaka-idea kapag marunong tayong gumamit ng summation notation. Dahil hindi pa rin tayo less than sa 0.05, so, gamitin ulit natin. So, ito naman. And, ang gagawin na natin, x raised to 5 divided by 5 factorial. And same process. We will have here on the 6th iteration or using 6th term ang ating Maclaurin series expansion. So we were able to have at the approximately 3 significant figures. So magkakaroon tayo ng percent of 0.015%. So less than na tayo sa ating specified acceptable error criterion. So, yun na yung ating value. And you will notice na hindi lang significant figures ang ating achieve. Nagkaroon na tayo ng hanggang 4 significant figures. So, near na siya sa true value natin in terms of 4 significant figures. Pero yung assumed natin lang ay significant figures using the criterion. So, getting back to our discussion, so, this is similar doon sa ating result. So, you can try it on your own using yung ating Excel.